Welcome to the Astrophiz podcast. My name is Brendan O'Brien, and first of all, we would like to acknowledge Australia's first astronomers, the Aboriginal and Torres Strait Islander people, the traditional owners and custodians of the land we are on. This episode is produced on Yorta Yorta country, and we'd also like you to influence your local politicians to do more to mitigate climate change by moving from fossil fuels to renewable energy sources. Our audio files and transcripts are available on our website at astrophiz.com, and our MP3 files can be freely streamed or downloaded to your favourite device from our SoundCloud channel, from Pocket Casts, our free Audible stream, YouTube podcasts and Apple podcasts. And right now we're zooming over 7 time zones right up to the top of the world to speak with a wonderful astrophysicist at the University of Helsinki in Finland, Jenni Häkkinen. Let's go. Hello, Jenni.
Hello, Brendan.
Today, listeners, we're lucky enough to be speaking with Jenni Häkkinen, a fabulous PhD candidate from Finland who has been working with a small team who have done a big thing. They have turned science on its head with their new paper in Nature Astronomy that changes our understanding of the fate of the Andromeda Galaxy and our very own Milky Way Galaxy. First up, congratulations, and thanks for speaking with us today, Jenni.
Thank you so much. Thanks for inviting me here. I'm very excited to talk about this topic with you.
It's a pleasure. So before we talk about Andromeda and the Milky Way, can you tell us where you grew up, please, Jenni? And could you tell us how you first became interested in science and space?
Yeah, sure. So I'm from Laukkala, which is a smallish town of about 20,000 people, a bit over 30 kilometers north of Helsinki, which is the capital of Finland. So Finland-wise, quite south of the country. I don't really remember if I had some really big epiphany about science when I was young. I do remember that I like to look at the stars. We have a family cottage sort of in a remote area in Finland where you don't have much light pollution and the constellations can be seen very well. I do remember that in school I was very early on good and interested in math and then physics and chemistry when that started. So I think the interest for space then also somehow started to accumulate from there.
Yep. Okay. Look, could you tell us a little bit about those school days at Vaskaveri Upper Secondary School and your earliest ambitions, and if those earlier ambitions changed and evolved and morphed over time?
Yeah, so Vaskaveri Upper Secondary School in Finland is for the ages of 15 to 18, so after elementary and middle school. And there you can choose these advanced studies that you study more of, and I chose math and physics and chemistry. We had really good science teachers in our school, and our physics teacher organized every year, I think, to the second graders trip to the Department of Physics at the University of Helsinki as a part of this voluntary astronomy course that we could take. And I think that trip really left an impression on me. And I had a few friends on my physics courses. And in the spring, when we had applied for university, we sometimes drove to the department to look at it and wonder if we all would be studying there the next fall. But that being said, I didn't originally come to university to study astronomy, and actually almost applied to study biosciences because I sort of was still looking a way to combine physics and chemistry, and I also got a little bit interested in biology. And I applied to the physics program in Helsinki because there was this option to do sort of a wide-ranging degree where you could choose multiple subjects to specialize on, and I was planning to combine physics and chemistry and biochemistry. But then during my first year, I took a theoretical physics, like a basics into quantum physics or theoretical physics course with some of my friends that I had made. And I don't know what it was in that. I was interested. Maybe I just wanted the challenge, but I sort of got stuck on that ever since, and then scrapped my original idea of doing this combined degree of physics and chemistry.
So specialising at an early stage. So after your successful school career, you did your Bachelor of Science in Theoretical Physics at the University of Helsinki, and there you continued your studies and you were awarded your Master of Science degree in Particle Physics and Cosmology, and now you're a bit over a year into your doctorate in Astrophysics and Cosmology. Now, for our early career researchers and undergraduates listening, could you tell us how you arranged it and why you decided to do your PhD in astrophysics and cosmology?
Yeah, those are some really good questions. So, like I said, I got into theoretical physics, and then after my bachelor's degree, I was really interested in cosmology, and I ended up doing my master's thesis on studying early universe gravitational waves, which was more of like this combination of particle physics and cosmology. I did like the project that I was doing, and I loved the research group I was part of. But for various reasons, when I was graduating and sort of starting to look into PhD opportunities, the funding situation and also the supervision resources was a bit unclear. And I had to start to look into other opportunities. Because of that, I also started to think what I would then like to work on. And I knew that I wanted to do something related to cosmology, and I knew that I wanted to do computational work. A lot of our studies had evolved around paper pen calculations, and I was very clear that that was not something I wanted to continue with. And during my studies, in my master's and in my bachelor's, I had done some additional courses on astronomy and galaxy formation, which is also very tied into cosmology and sort of from another point of view than particle physics. And I think then just by luck and good timing, my current PhD supervisor was advertising this position on some emailing list which had the astronomy students on it. And I answered the email, expressed my interest, and ended up getting the job.
Oh.
Then maybe sort of why I decided I wanted to do a PhD. That wasn't something I came into university with in mind, but I think by the time I was graduating with my master's, I didn't have any clear plan to what I would want to do if I left university. I really liked doing research and I was interested in learning more about the world. And I also like the idea of having a few extra years to sort of figure out what I would then like to do. And then when it started to look like that I could do that by moving into astrophysics, that kind of felt like sort of a nice moment to think back onto my younger self in that voluntary course in astronomy in high school. And I thought that this is cool, but maybe not something that I could make a career out of.
And you've certainly launched it with this latest paper that's been published. That's so cool. So the plan for today is to look at your PhD studies and get an idea of the techniques you've used to measure the vectors and movements of nearby galaxies, then have a look at your work on Andromeda and the Milky Way galaxies and how your team has given us a new insight into the fate of our home galaxy, the Milky Way. How does that sound, Jenny?
Sounds really good. Let's get into it.
Okay, so first we'll have a quick look at your PhD research to help us understand your personal research trajectory. It looks like you're focused on three main areas. One, you're using simulations. Two, you're looking at galaxy evolution. And three, You're focused on our local group of galaxies. Now, could you give us a brief outline of each of these three elements of your PhD research, please, Jenny?
Yeah, for sure. So simulations, I think, work together with observations. So we have satellites and telescopes that look into the sky and observe the objects that are moving there. But then there are limitations to those machineries. And I think simulations are a way to extend what we can do with observational techniques. So they definitely work together.
Yep.
For instance, we cannot see what's directly behind the plane of the Milky Way Galaxy, but simulations predict for us what could be there.
Yep.
And what I'm doing is I'm looking into the future of our galaxy and the nearby galaxies. And well, obviously with observations, we cannot go there. So simulations help us extend into that realm. What kind of simulations I use are these idealized simulations where we put an object in isolation to the simulation and let it evolve. And then also I use cosmological simulations where the simulation includes a cosmological surrounding for our system and it expands in time like our universe does and has the properties that we expect the universe that we are in has. And I could mention that we use high performance computing because the simulations are really large. They need a lot of resources and a lot of memory. So we run them usually on supercomputers, which have more processing power than the laptops we have at work. Then galaxy evolution, which is very often studied with simulations, combines cosmology. So what we know, sort of the theoretical framework of the universe that we're in, with some initial conditions for our galaxies. So what kind of form we expect our galaxies to originate from. And then a ton of physical processes that I'm still trying to learn better, but like general relativity, hydrodynamics, electrodynamics, a lot of things. And it's a little bit messy, but you have these different concepts that work together. And then, like you said, I focus on the local group of galaxies, which is the galaxy group that consists of our galaxy, the Milky Way, our neighbor galaxy, Andromeda, and then about 100 known lower mass galaxies, such as the Triangulum Galaxy and the Magellanic Clouds.
Cool. Thank you. Look, just to follow up on that, what are the big questions you're asking for your PhD and what problems are you working on that you have to overcome?
So now I think the biggest question that I'm trying to ask and what we have already been trying to ask with the previous paper is how certain we can actually be about the future of the local group. It has been sort of a textbook knowledge for a bit over a decade that the Milky Way and the Andromeda will collide in about 4 to 5 billion years. And our most recent study, which we can talk about later, found that this might only be about a 50-50 chance of the merger, of the head-on collision happening. And now what I'm trying to do is try to figure out how certain we can be about the prediction of the merger and what kind of things affect the uncertainty in it, especially how do the surroundings of the Milky Way and the Andromeda affect the merger. And for this, I need the cosmological simulations, which include the environmental effects of these galaxies. And we have found some interesting problems with this because no one's ever looked into the future before, at least not in this extent. So running simulations past redshift 0 has been interesting, and we found some issues that we have not encountered before. So there has been a lot of debugging in that, but it is most certainly really interesting to see what we find out.
That is awesome. New problems. So exciting. Thank you. So, look, that brings us now to the team that you worked with to produce that beautiful Nature Astronomy paper. It must have been so much fun. and incredibly hard work by the sound of it, working with such a skilled team. Now, would you like to mention some of the other team members and the specialist skills that they brought into the project?
Definitely, I would. So firstly, I have to mention first author on the paper and my supervisor, Til Savala, who came up with the idea for the study and also wrote and did a lot of the actual analysis on the project. Then I would also like to mention Jehan Delhamel, who at the time was a bachelor student in the University of Toulouse, France, and was doing a few months long internship as part of her studies at our university. And together with Till, they did like the majority of the analysis for this paper.
Yep.
And then I could also mention my fellow PhD colleagues in our group, Atte Keitanranta and Alex Rawlings, who really worked on the calculations of dynamical friction that we use in this work. And then also with Alex, we did n-body simulations to validate the method that we were using in the paper.
Awesome. And you got the results out. Now, thanks, Jenny. Now, before your paper was published, as you mentioned, the accepted view was that our Milky Way and the Andromeda Galaxy were destined to collide at some time in the distant future, 4 or 5 billion years. Can you tell us a little bit about the techniques, the models, the observations that you used to demonstrate that such a collision can no longer be viewed as a certainty?
Yeah, so I think what's also partially really cool here is that we do use similar techniques that have been used before. So we refer to what we do in the paper as a semi-analytical analysis, which essentially means that we use a numerical orbital integration for the orbital evolution of our galaxies, and then combine that with an analytical description of dynamical friction.
Yep.
We have modified, like I said, Atte and Alex worked on a lot on the calculations for the dynamical friction. And with this, I mean that we used a modified version of the friction where usually in the standard scheme of dynamical friction, you have to assume that you have a more massive host galaxy and a smaller satellite galaxy that's orbiting around it. But in our case, when you look at the Milky Way and Andromeda, it becomes a bit difficult to say which of these galaxies would be the host and which would be the satellite. So we tried to account for that in our analysis. What is also different to what's been done before is that for this paper, we do use updated observational values from the Gaia satellite and its third data release. And also on top of that, usually what has been done is that these constraints from observations are being used so that you take the mean value of the observation, like what is the proper motion of the Andromeda, and you take the mean value of that, so the most expected value. But what we did is that we made thousands of Monte Carlo samples from the whole parameter space, so including all of the observational errors that come with these parameters. And from that parameter space, we sampled different kinds of technically possible initial conditions for our galaxies. And then that gave us the updated prediction of this 50-50 chance. And then in addition, we included up to 5 Gold group galaxies. So usually, like a lot of studies have been made about the 2-body orbit between the Milky Way and the Andromeda. And then also 3-body orbits with including either the 3rd most massive local group galaxy, the Triangulum, or then the 4th most massive one, which is the Large Magellanic Cloud. But we did this study with 2-body orbits, with 3-body orbits, then with 4-body orbits, including all of those 4 galaxies, and even 5-body orbits, which included additionally the smaller Magellanic Cloud. So I think it was a combination of what's been done before with some maybe broader way to look at the situation.
Wow. Standing on the shoulders of giants and coming up with really creative ways of looking into the future. That is beautiful science. I really love it how science is not set in concrete and how you've demonstrated our understanding of our universe and our place in it can be refined when we find new evidence. And you and your team have done exactly that. And so big congratulations. And your team must have been so excited to go through that rigorous peer review process and end up being published in Nature Astronomy. Are you all still in the afterglow from that achievement?
When the paper was published, it did get a lot of media attention. And I think, well, at least I was like, I knew that it would be interesting to the public, but I think I was still a bit surprised sort of how big it came at the time. For me, this was my first ever paper that I got to be a part of. So that was quite big as well. And then we had people in this project working from different institutes over the world. So it was also cool to see how the results were being talked about in not just in Finland or just in Europe, but in North America and in Australia. And sort of, it did feel quite amazing to see how interested everyone was in what we did. But I would say that right now the focus is on the follow-up paper, which is my project, and we want to do these cosmological simulations that include more realistic physics and see if we actually reproduce this result that we found out with this more simplified approach, or if we just end up confirming what was known before. Really can't say at the moment, but I think that's where the focus is really on right now.
Awesome. I can't wait to see that follow-up paper. Thank you, Jenny. Now, you and I live on opposite sides of our planet. You're way up north, up near the Arctic Circle, and I'm way down south, down under, in southern Australia. I live way out in the bush under beautiful dark skies, and we often look up at the wonderful Magellanic Clouds, which are actually nearby galaxies, as you've mentioned. Does your PhD research tell you how my view of the Magellanic Clouds will change if I live for a few more million or billion years?
Oh, that's a really good question. Well, we do look at analogs of the local group in our simulation, so systems that could represent the galaxy group that we're in. And in there, we also look at analogs of satellites of Milky Way and Andromeda, which the Magellanic Clouds are, and whether or not they, for instance, merge with either of these galaxies before the Andromeda and the Milky Way would merge. That being said, this is more of a statistical study that we're conducting. So we're looking to have thousands of these analogs and to see on a more of statistical premise how likely different scenarios are. And I think we can say maybe something about that. We find that in this many cases of our full sample, we find that the Large Magellanic Cloud would merge with the Milky Way, but you still cannot sort of say that that would be an exact analog of the Large Magellanic Cloud that is on the sky. I know that some people are also doing simulations on that where they try to find the exact analog of the galaxy. So there are things like the position of the galaxy with respect to the Milky Way and hydrodynamical composition and stuff like this, which our simulations do not necessarily take into account. So I want to say yes, but I probably cannot do that, unfortunately.
And that's the way science works. Thank you very much, Jenny. I would love to see that in the future, but I fear my chances of seeing that the laws of biology are in the way. Okay, we're up to date now. We know very well science doesn't always sail smoothly, and we can keep our propeller heads on for a short time. Is there a particular part of your PhD research that you're working on right now that's driving you crazy or is astonishingly exciting, or perhaps both?
Yeah, there have been multiple challenges along the way. Like I said, we're running the first simulations of this kind into the future. And like one funny, in quotation marks, a problem, which didn't end up actually being a problem, was that when we looked at the positions of the galaxies in the simulation, they seemed to go over the actual physical box size of the simulation. And we were really confused about that for a day or two. And then eventually realized that because we're looking at things into the future and the simulation is expanding, the box is also expanding. But usually you look into the past, which means that the simulation box shrinks. So there are things like this which have been kind of funny to realize. And we're also creating our own simulations instead of using pre-existing ones because there are no into the future. And it's just slow to debug and analyze. So usually you try something and then you put your simulation to run and then it queues for a little while with this in the supercomputers and then it runs and then it crashes and then you do this again. And I've been now debugging my newest simulation, which is bigger than the previous one we did for 2 weeks now. And it is slow and it is hugely annoying, but also it is like a part of this job that you get a new error message every now and then you get excited again and you have a new problem to solve. And I think it's just something that you have to accept when you're doing this kind of work.
It sounds like you're on a roller coaster there, Jenny, debugging. And what about the nature of your non-research work? We can take our science hats off for a little while now. Do you have any other responsibilities as a PhD candidate at the University of Helsinki? Like, do you do tutoring or do you teach undergraduates?
Yeah, in our university, most PhD students are also teaching assistants during terms on courses, and I've been a TA on the cosmology courses for a few years now. And it's a lot of work sometimes, but I think it is also really cool to have that sort of first experience into what teaching is like. And then also to talk, most of the students, at least on the courses that I've PA'd, are really interested in the things. And it's fun to talk about these things with the undergraduate students. I've also been already in my bachelor's and master's studies quite involved in student governance at the university and doing student representative stuff at like program boards. And I'm currently on our doctoral program board, one of the student representatives. I think I really like that. I've liked being able to see a little bit behind the scenes on what's going on there on the like side where things are being decided on about what it's like to study at the university. And also it has allowed me to get more familiar with the staff and take a little bit responsibility there. And I know some people who also can be co-supervisors on like bachelor thesis projects or something like this, but I haven't done that yet myself. And then like one of our responsibilities is to do our own courses, which are part of the degree that we are completing here. And I think for many of us, we would just like to do the research all the time, but it is probably good to have a little bit of the core stuff there as well to back up the knowledge.
Variety, the spice of life. let's get back to your work. As a PhD researcher, we've heard that you're necessarily immersed in solving some of the most complex and puzzling phenomena of our universe. Now, how do you do your best thinking? Like, what circumstances do you usually need to swim clearly through that sea of data and come up with verifiable conclusions? What situations and surroundings support your best thinking? For me, it's chocolate.
Chocolate is good. I think for me it has to be coffee, which is a very Finnish thing. Drink a lot of it. I think, for real though, I think it is a combination of working with other people and working alone. I like that we have a research group of about 10 people, and I have worked on a few projects already, and it's nice to sit down with people and debug a code or think what to do next or solve any problems in general. My coworkers, I think that is really a key factor of doing research is to do it with other people, and I really enjoy that. That being said, sometimes when there is just a lot of mechanical analysis work to do, I do like to put on some noise cancelling headphones and a Pomodoro timer or something similar and just stare at the code and do it in my own sort of cloud with some good music. So I think it is a combination of those two, but I do really like going to the office, even if I would work by myself. There are some days to then have breaks and so see my coworkers and my friends and sort of have something other to think about than just the physics that I'm trying to solve.
Fantastic. Again, we're coming back to variety. Thanks, Jenny. Now, when I look back and looked at your education profile, I noticed that you were working on your first science degree when the COVID pandemic was peaking back in 2020 and 2021. Now, how did COVID affect you and your family, and what was the impact on your studies? Were there lessons learnt?
Yeah, like for probably most of the people, I saw my family and friends a lot less. I lived alone at the time, so I did spend sometimes even weeks just in the apartment by myself, and I can say that that was a good factor on my mental health.
Yep.
So then I was sometimes studying, but then sometimes doing like summer internships in research groups as a research assistant. And I did find out then that I cannot work remotely for long periods of time. Like a day or two is fine, and I can probably be a very productive. But then when I had been home for weeks sometime sitting at my desk alone, it was sometimes really difficult to get the work done, even though I was interested in it. But that was the experience for me. It was difficult. And I did also then realize that I need a desk at home because I only had my kitchen table that I used to work at then. And that was not a good solution, I have to say.
Very good, thank you. Ah, look, you've painted that big picture of simulations and galaxy evolution and using some supercomputers. We've looked at your PhD research and we've looked at your, very briefly, at your follow-up paper, and we wore our science hats there for a while. Could you now tell us a little bit about some of the things outside of your PhD that regularly bring you great joy, Jenny?
Yeah, yes, I would be happy to. Like I said before, I enjoy going to the office to see my colleagues and friends. And I think also having those connections and seeing those people in the office or outside of the office is something that I really enjoy. I do have some hobbies of my own. I've done most of my life a Finnish folk dancing. I think since I was about 4 when my mom put me into one of the classes. And it is like one of my favorite things still. And I love the group that I'm part of now and the group that I was part of when I was younger. I think the best part of that has been to get in touch with the traditional customs of the Finnish people, in addition to the actual dance itself. Then a year ago, I took up ITF Taekwondo, which was intimidating at first, but I've really come to like it. And I hope that I can continue to do it for a long time. And then sometimes I like to just be by myself, and then I usually read fantasy books or science fiction. And then also I have a Nintendo Switch that I like to game on. At the moment, I'm really into Stardew Valley, which is a very relaxing sort of get your mind off of other things. Yeah.
Yep. That's fantastic, Jenny. Thank you. I'll have to look up and find out a bit about Finnish dancing. It sounds beautiful. Okay, so you've done some teaching assistant work as a teacher of both graduates and undergraduate students. Is outreach an important part of being an astrophysicist?
I do think so. I think one of the main points of doing science is to communicate it to the public. We can have goals of doing science to advance in technology or advance in medicine, but then also I think kind of science that we do in astrophysics is more of the trying to find out as much as we can about the world. And I think that the goal is not to do that, to have that knowledge by yourself, but to also share it with the people who, for one reason or another, cannot be doing that. And I do think it is almost like a responsibility for a scientist to communicate what we are learning about the world to the general public.
Fantastic, and you're doing exactly that as we speak. Thank you very much, Jenny. Okay, we've reached the point where finally the microphone is all yours, and you've got the opportunity to give us your favourite rant or rave about one of the challenges that we face in science: inequity in representations of diversity, or in science denialism, or science career paths, or your very own passion for research, or that huge human quest for new knowledge. The microphone is all yours.
Wow, thank you, Brendan. This feels like a big responsibility to choose what I could speak about. So there was a lunar eclipse this week, and I think that was a very concrete reminder for me about space and about the fact that what we are studying are actually real objects. I think it's really too easy to forget when you do your everyday work and you look at your simulations and you have some particles there, and that gives you some information about your system, but it gets easily sort of mechanic. And I think it's easy to forget that those objects that we're looking at in our computer screens are actually out there in the world, at least for the type of research that I'm doing. And I just think in some ways it's scary, but I think it's really beautiful to think how small we are in the context of the universe. And it's still it's difficult for me to wrap my mind around, like when I was looking at the lunar eclipse and at the moon, to think like that object is actually out there in space. And those galaxies that I'm following in my simulations are actually out there in the space, and that we are in one of them. And I don't know, I think it's really, really exciting. It's really beautiful in some way that human society has advanced to this level that we are able to study these objects. We're able to try to understand where we actually are, because I think in some ways we still don't exactly know in the larger scale of the universe. And I don't know, I get a bit overwhelmed when I start thinking about it, but I think it's a good reminder for a scientist and astrophysicist to every now and then remind yourself that these interesting and cool things that we're looking at are actually, I mean, if you're an observer, this is probably much easier. But at least when you do like theoretical work and work with simulations, it is easy to forget. And I think it's a really nice thing to remind yourself that it is just astonishingly cool that we are able to do this and study these things.
Thank you, Jenny. You are certainly keeping it real. Okay. Is there anything else we should watch out for in the near future? What are you keeping your eye on?
Naturally, I'm keeping my eye on the next data release of the Gaia satellite, which is giving us more information about the motions of the objects in the local group of galaxies that's planned to arrive in late 2026.
Yep.
Yeah. And something else that I think that I'm not working on, but I think really exciting, which is also planned to arrive in late 2026, are the results of the Euclid satellite, which has been now in space for a bit over 2 years. And it keeps mapping the sky for a 3D map of galaxies. And I know that some data has already come in, but I think there's more data coming. And Euclid is trying to answer big questions about dark energy and dark matter. And I think that is something that I'm very excited to see. And then some people in my research group are working on supermassive black holes, which could produce gravitational waves. Very loosely connected to what I did in my master's, but there's a really big science project on that front called LISA, which is planned to be launched in maybe about 20 years, that should observe gravitational waves in space. So I think that is also something people should keep their eye on.
Okay, Gaia, Euclid, and Lisa. Keep your eye on it with Jenny. Well, thank you so much, PhD candidate Jenni Häkkinen. On behalf of all of our listeners, and especially from me, it's been really exciting to be speaking with you way up there in Helsinki and to hear about all of your discoveries, to celebrate your first paper and to find out about your follow-up paper. Thank you especially for your time. I know you've got a grueling schedule and under the pressure to analyse all that high-performance computer data. And good luck with all your next adventures and all your future travels. Now, listeners can tune in to Jenny's research. It's all easy to find. It's on tinyurl.com/JenHäkkinen. That's JenHelsinki, all lowercase, all one word. So check out Jenny's research. May your career continue to be out of this galaxy. I can't wait to see that follow-up paper. Thank you, Jenny.
Thank you so much, Brendan. It has been a pleasure to chat with you. And yeah, I can't wait to see what comes next.
Awesome. Good night, Jenny.
Good night, Brendan.
And remember, Astrophiz is free, no ads, and unsponsored. But we always recommend that you check out Dr. Ian Musgrave's Astroblogger website to find out what's up in the night sky. See you in 2 weeks. Keep looking up. Radio Wave!